Hello, welcome back to a brand new video of the same old course, which is Matlab simulation course. We are going to start a new course known as Power Electronic Simulation on RAM in a Matlab. So in this, what we have to do, we have to make a buck converter. I don't know what is buck converter. We have to make a model fidelity. I don't know what is model fidelity. I know what is feedback control, and we will go to conclusion. So it is about 30 uh, 50-minute long course, and we will easily uh, do this course without needing any basic concept of electronics. If you have studied the electronics in 9th, 11th, 12th, that will be the perfect basic for this course. Okay, but you have to understand this course to know about the simulations or simulink. So let's start with the course. Obviously we will do the course in a browser because browser is much faster than the PC. And currently in India the temperature reach up to 40 degrees Celsius, and my PC is currently at 40 degree. So if I use Matlab in this temperature, it will going to burn the whole setup. That's fine. So let's start with the course. So let's start with the course
Hello,
overview.
and welcome to Power Electronics Simulation On-Ramp. This course will introduce you to simulating power converters using Simscape Electrical. Power electronics are everywhere in the increasingly electrified world we live in today. But not all power is created equal. Power must first be converted from one form to another, such as between AC and DC. Whether you are working on electric vehicles or laptop computers, power electronics devices perform these conversions. And power electronic simulation is a crucial step when designing these converters or the systems that use them. In this course, you will learn how to simulate a buck converter circuit using Simscape Electrical. Then you will explore how you can choose between detail and simulation speed by creating other circuit representations. You will also learn how to simulate closed-loop voltage control for the buck converter. You don't need to learn a lot of theory to start simulating power electronic circuits. But it will help if you know a little bit of Simscape, just the basics. Like setting block parameters, and how Simulink and Simscape interact. If you've never used Simscape before, it's easy to get started. And we recommend you first take Simscape On-Ramp to get you up to speed quickly. Throughout the course, you'll be completing tasks in the Simulink editor. It's the same Simulink environment you'll encounter outside of this training, but with a few added features. Tasks will appear on the left and feedback on the right. If the assessment involves a simulation value, it will be displayed in the feedback area as well. Enjoy the course!
So let's start with the power simulation.
Power electronic devices convert electricity between what you have at a source and what you need at a load.
Okay.
The conversions can go from DC to AC, AC to DC, one DC voltage to another, and one AC magnitude and frequency to another. The key feature of all power electronic devices is that they're controlled by high-frequency switching.
Yes.
These switches are built using semiconductor devices, such as transistors and MOSFET.
So currently, if you ask what we used to switch at high frequency, so at present we use MOSFET because transistor is an old technology which has a problem like heating, and the IC, basically the IC is the collector current. It is not very stable because of the value of beta. That's why we use MOSFET, and MOSFET are also old technology because currently we are using a CMOS MOSFET. You can know as NMOS or CMOS. Okay, so these are the basic components of electronics. It's nothing, it's act like a switch, but this switch can develop a different type of circuit, as you can take example as op-amp, which is made by just the combination of transistor and resistor, or the basic the modern processor like our Intel processor or AMD processor, which is made up of complex design from the MOSFET. So that's a different part of electronics, but you just have to understand that the basic switching that we use to control the power is from MOSFET or transistor. That's the basic concept. Okay.
Switching minimizes the device's power consumption, since power only flows when the switch is on.
So basically, if I connect a pipe to my water tank and the other side of pipe is open, so if I open my tab, the water will go in the straight direction without any problem, and at that point I can say that I have a full potential. Okay. But what if I just no, what if I just turn on tap and close, mean if I open or close the tap fast, very fast, so what will happen, the potential at the end of the pipe will reduce based on the speed at which I am uh, closing or opening the tap. So electricity is also like a flow of electron, but the flow of electron and the electric field are in a different direction. But if you control the switch by logic code or whatever, it can also control the flow of electron, and hence the electric field can also be controlled. So that's how we convert the power, like AC to DC or DC to AC, or AC to different types of DC, or different DC to single type of DC, like that.
However, in numerical simulation, this high-frequency switching can be difficult to capture. And this is because of the large discrepancy in timescales between the switching and the dynamics of the remainder of the circuit. With Simscape Electrical, you own the choice. You can include the detail if it's relevant to your design, or you can speed up your simulation by choosing a coarser model. Building simulations with Simscape Electrical is as easy as drawing a circuit diagram. The electrical library contains all the blocks you need to model common power electronic devices, from the individual circuit components to pre-built converter blocks. You can choose from several variations of blocks that model the converters, switches, and switch drivers. These choices let you control the detail of your simulation. As you'll see later in this course, making purposeful choices about the level of detail is crucial in simulating power electronic devices. In the next activity, you'll see an example of a buck converter, a DC to DC converter where the output voltage is lower than the input voltage. The model uses a pre-built block from the Simscape Electrical library. This block is optimized to produce relatively fast simulations while still capturing the important dynamics. Later, you'll explore the buck converter in more detail and compare ways to model it in Simscape.
The first task is to connect the PS step block to the PS step block with the physical signal port R. PS step block, the physical port R. Okay. So the block is already there. Let's zoom the circuit, and here there is a constant block which is the voltage source. It is connected to the comparator, and comparator is connected to the PID controller. PID controller is a type of controller which can control the signal via feedback, and it can control the signal with probability, integration, and derivation. After that there is a rate transmission, then there will be a PWM generator. So basically the voltage is going to rate transmission. Rate transmission is connected to the PWM generator. PWM will generate the PWM, and that will go to the buck converter is the fast switching. So if the value of PWM is set to 0, the switch will be off. If the value of PWM is set to 1, the switch will be on. And based on that, we will get our voltage here, and based on that voltage we can decide the value of PID controller. Okay, so this is called as a control system tuning. Now connect the PS step block to the physical signal R. Physical signal R is a variable resistor. Okay, next double click the buck converter block and open this block parameter. Connection. Okay, so the block in the block parameter we have to change the inductance to conduction resistance. It's inductor LC filter. Inductor to 1.3 into 2.5 E, 1.3 into 2.5 into 10 raised to power minus 4. Next session. Skip review. Simscape review. This chapter will review the basic of adding components using sensor block and setting initial values. If the activities are unfamiliar to you, or if you want additional background information, take the Simscape online. Okay. So in Simscape there is an electrical library where you can find the electrical components. In that also there are some block parameters. Capacitor. In capacitor the voltage lead and the current lags. Okay. In inductor there will be opposite of the capacitor. There the current will lead and the voltage will lag, and we need two types of sensor to find out the values. Okay,
As you saw in the previous simulation, a buck converter is a DC to DC converter that decreases the voltage from the input source to the output load. Buck converters are common in personal electronics, charging devices, hybrid vehicles, and more. Imagine, for instance, that you're using a solar charger to charge your mobile device. This solar panel has an open circuit voltage of 15 volts. However, USB charging has a maximum voltage of 5 volts. It's important to buck the voltage to a lower value before connecting your device. Otherwise, it might just explode. Before we build one in Simscape, let's briefly review how a buck converter works. Again, the goal is to convert a high DC voltage to a lower DC voltage. Of course, a simple way to do this is to just use a voltage divider, but this is pretty inefficient. Instead, by rapidly opening and closing a switch, you can get an average output voltage that is lower than the input. Kind of like pulsing a rocket booster off and on to get just the right amount of thrust. This is a technique called pulse width modulation, or PWM. For a PWM signal, the fraction of the time that the signal is high is called the duty cycle.
Okay.
When the duty cycle is constant, the average voltage across the switch is just duty cycle times the period. So now we have an average output voltage that is lower than our input voltage. But wait, the maximum voltage is still higher than our load, the phone, can tolerate. Plus, these fluctuations don't make a particularly useful signal. What we need now is something to smooth the high frequency pulses into
So
something that looks close to a constant DC value.
we will use capacitor or
Something like
inductor.
a low pass filter.
Yes.
Adding an inductor and a capacitor to your circuit smooths out the high frequency switching, leaving behind a signal that's nearly DC. The complete buck converter circuit also includes a diode, so current can continue to flow while the switch is open. The relationship between input and output voltage, switching frequency, and component sizes all factor into the design of the buck converter. The simulation lets you quickly iterate through designs without ruining your phone. Simulink and Simscape make building these systems simple by providing blocks that model each of these circuit elements. In particular, the switching and filter elements together are available as a single block. In the next activity, you'll explore this block and its parameters, and learn how to model a buck converter circuit from scratch.
The task is add a buck converter from Simscape electrical semiconductor and converters library. After that, double click the block to open the block parameters dialog. Set the following parameters. The threshold voltage should be 0.5 volt. Inductance should be 250 millihenry, and inductance resistance should be 0 ohms. So the output impedance will be very low, and the capacitance will be 50 microfarad. Threshold voltage should be
Or if you have not already connected the solver, then connect the solver to any port of a SimScape library. SimScape mechanical the constant block value to it is set to 2.05, 0.25. Why it is doing that? Let's see the solution. Constant value is set to 0.25 as it is. Resistor value is set to 2 ohms. Shit. Back. See the solution. So I have successfully connected everything here. Next, the product requirement transistor R. Hint. Double click the constant parameter. Yes, double clicked already. Okay. You can see the value is set to 2 ohms.
Imagine you're playing a drawing game. Your prompt is to draw a person singing, and others need to guess what it is before time runs out. You'll probably draw something like this: quick, symbolic, and it gets the point across. Meanwhile, your opponent Leo is working on a masterpiece. It's way more realistic than your drawing, but oh no! The timer went off, and no one was able to guess what he was drawing. Your drawing and Leo's are two examples of fidelity, how closely a model represents the real-world system. A low-fidelity model loosely represents the real-world system. It may make coarse approximations, like ignoring friction, transient behavior, or your singer's nose. Low-fidelity models typically give broad, representative characteristics of a system and simulate quickly. They can be useful, for instance, if you need to model a component's input-output behavior within a larger system. A high-fidelity model closely represents the actual system. It may consist of many parameters that can be tuned to capture fine details. It might be tempting to always choose a high-fidelity model. After all, it's more accurate. However, they often require significantly more computing resources and might not always be appropriate for the situation. For example, this drawing might be museum quality, but it won't win you the game. When modeling power electronic circuits, it's particularly important to choose the appropriate model fidelity for the purpose of your simulation. In particular, because of the high-frequency switching that defines power electronics, the device outputs exhibit both a slow overall response and a much faster oscillatory behavior. This is known as a stiff system and can be difficult for numerical tools to solve. Therefore, it's common to choose lower fidelity models when applicable to improve simulation performance. In fact, the buck converter that you modeled in the previous activity included a common approximation, modeling the switch using piecewise linear equations rather than capturing the full nonlinear behavior of each switch event. By choosing other parameters or blocks, you can also choose coarser representations, such as averaging the PWM behavior, or ignoring the circuit components entirely and modeling a fully idealized DC-DC conversion. If you need a higher fidelity model, you can capture the full nonlinear switching behavior by creating a model from individual circuit components. There can be orders of magnitude differences in the computation time for the various levels of fidelity. Therefore, you should always choose the simplest model that captures the dynamics of interest. In this lesson, you will represent the buck converter at the levels of fidelity just described: behavioral, averaged switch, and fully nonlinear. In doing so, you'll be able to compare the available parameters, resulting simulation detail, and computation time. You'll also learn some guidelines for when to choose which level of fidelity.
Add a buck converter block to the model connected to the voltage source and a load. So far you have buck converter, three level of fertility, a behavior model using the average value DC to DC converter block. An average switch model use the buck converter block with the switching device and set to add average switches. And the buck converter, a previous linear switch model use the buck converter block with the switching device set to the ideal semiconductor switches. Okay. Okay. So add an inductor and a capacitor from the SimScript library. Inductor foundation library. And we have to use the inductor and capacitor. Set the value of the inductor to 250. 250 microhenry. The value of the resistor should be 50 microhenry. 50 microfarad. Next, add an N-channel MOSFET and a diode with add an N-channel MOSFET and diode with both SimScape electrical semiconductor and converter library. Set the following parameters for each block: N-channel MOSFET, drain source or resistor, RDS on. And IGBT. Okay. N-channel MOSFET. The N-channel MOSFET. We have to do some settings like we have to set the drain source on resistance. Okay, so on resistor pin 11.7E 3 ohms and gate source threshold voltage 3 volt. So set it to then we have set the value for forward bias and the reverse bias. Forward voltage the resistor should be on resistance should be 11.7 of conductance should be minus 5. Next, connect it like this. Make the connection match the circuit diagram. So, connected to this part. Capacitor plus connected to this. Semiconductor and converters. Okay. The gate driver block. Change the input port parameters to electrical. Leave the other default parameter unchanged. add a control PWM voltage block. Set the PWM frequency to 101 kilohertz. Kilohertz. Okay. Connect the PWM port to the connect the PWM port to REF. The PWM sorry. Connect the PWM port and REF ports on the controller. Connect the PWM voltage and the gate is converter block. So the board so that the set the duty cycle of the PWM voltage which is set to U. Starts connect the G port of the gate. Connect the G port of the gate driver to the gate port currently on the gate driver to the source port of the connected to the source port of set the solver to ODE23T. Set the solver set the solver to ODE. The solver to ODE23T. ODE23T. Apply. Next. Oh. Comparing the model fidelity option, non-linear, device linear, average linear, and behavioral.
In practice, all power electronic components must be regulated using feedback control. Feedback control allows the converter to appropriately handle fluctuations in the input or load. Standard techniques such as PID or lead lag compensation can be used to regulate a buck converter. In this course, you'll implement a PID controller to maintain a specified load voltage, although the same modeling techniques apply to current controllers. The controller automatically adjusts the duty cycle of the switch based on the error between the desired and measured voltage. To implement PID control for a SimScape model, you'll need a sensor to measure the output, a reference signal, an error computation, a PID block, and a converter block to interface SimScape and Simulink. Then simply make the connections, enter the appropriate parameters, and you're done. In this lesson, you'll include a few additional implementation details. For example, you'll capture the analog to digital conversion using a rate transition block. This block samples a signal at the rate specified. When connected to a signal originating from a SimScape sensor, you can view this as sampling a continuous time signal at a discrete interval. In other words, an analog to digital conversion. You'll also use the PID block parameters to implement controller anti-windup and output limits, and account for the different sample rates between the controller and PWM generator.
So now we have to add a feedback PID controller and some comparator. Voltage source. I should have to add a voltage. Okay, I have to add the voltage sensor. Voltage sensor block. Now what I have to do? Connect the voltage sensor so that it matches the load resistor as the positive value, then connect it to the mesh. Sets the load resistance to the positive value, then connect it to this. Now set the sum block listed as a sum block. Delete the constant block connected to the PWM controller. Add this Simulink block to your model. Step block, sum block, this DISCR PTE PID controller. Set the sum block to plus minus. Plus minus. Add two rate transmission block. Rate transmission block. Signal. Rate Now we have to connect the reference. So the step will work as a reference block. Reference, comparator, controller, rate transmission, feedback coming from the output. Sorry, I have to rotate this block first. This back. The final step time should be 0.2. Step time should be 0.002. Initial value should be 12. Final value should be 6. That's all we needed. Next, now we have to go to the PID controller where we have to adjust the value of PID, that is probability, integration and differentiation. Okay, let's set the value of probability, which is 0.10. Integral I should be 352, and derivative D should be 7.6 into 10 raised to power minus 6. The filter coefficient should be 1.4 into 10 raised to power 5. Sample rate, so sample time should be 1 by FSW. On the rate transmission block, okay, so wait for a minute, I have to attend a call. Now on the rate transmission block, that is the feedback path, output port sample time should be 1 by FSW. Submit. With this we have completed our full course. Just kidding. Okay, with this we have completed our full course, but there is some part that we have left it. We have to complete that part, and that part is likely not completed because of some issues, so we'll come over with that issues. So we can finally complete our full course, the buck converter exercise, obviously. So I will complete this portion with the solution part. I have to add a buck converter here. Buck converter, then I have to set the value. The threshold should be 0.5. Offset inductions should be same. Also have to be same, but the inductance should be 250 microhenry. This should be 50 microfarad, and The last one has to be as it is. Okay, next. Now let's go to the next thing, that we have to add the DC voltage source from the elect found foundation, from the foundation library DC DC voltage source from the foundation library, and then we have to set the value to 48 volts. If we set its constant voltage to 48 volt. Next, we have to add plus to plus and minus to minus with a referral ground and obviously a follower. Next, add a resistor on the foundation library and set the value to 2 ohms. 2 ohms. Okay, so you can see I'm going with the flow. So if I get any type of problem again, that's not my problem. Okay, control R. Next, now here what we have to do, we have to add a PWM, sorry, PWM from Simscape Electrical. Simscape Electrical Control plus width modulation. Yep. After that, we have to PS converter. Take this converter here, we will convert it to the, no, we have to add a Simulink to PS converter. We have to add the G part. After that, we have to add a constant block. This. Then I have to add 1 by F SW. This, and this should be 1 by F SW by 100. Apply and OK. Next part, solution. Constant block has to set to the value 0.25. Why am I getting the problem? No, this time there is no problem. Okay. Next, in the configuration, again I have to set the configuration to T. Am I right? Yes, I have to set the configure to T. Then I have to click on apply and OK. Submit. Now with this we have completed the full course. Okay, and the best part about the course is taking the certificate. So let's take the certificate. Tomorrow we will go towards the next course, that is power system simulation on RAM and battery simulation on RAM, which are a fascinating course that every electronic student have to do to understand what is really mean to be an engineer. Documents and math certificate 32, 33, okay, 33. Okay. So that's for all today. We'll meet again soon. Till then,